Welcome to this presentation on two-dimensional elements, and we're going to be developing those. We've looked at one-dimensional elements, so moving on to the second dimension here. So for the setup here, there's no additional files beyond the notes, so if you want to go check out the notes, you can follow along there. They're in the notes folder, and the link is in the description below. So where are we headed in this overall, what we're going to be doing in this presentation, we look at rectangular elements first, look at linear and non-quadratic rectangular elements, look at triangular elements and linear as well as quadratic triangular elements, look at axisymmetric elements and the value of those, and then isoperimetric elements. All right, so you can see where we're at here. And again, in the description below, we'll have the index of the times of when each of these are, so you can skip ahead or move around as you need. Oh, sorry, and ANSYS elements as well. And basically where the ones we're talking about above, show up in the ANSYS elements. Introduction. All right, so we're going to be looking here as the heat transfer through a fin. And we've looked at this before in previous presentations, but what we're going to look at this time specifically is we have the heat that's moving in the x direction, but also in the y direction. So we don't have like a pin fin, very, very small fin, but we do have a fin that's got this 2D piece to it. So that's why we can look at 2D elements on our fin. So the temperature varies in both the x and y directions, so we're going to use these 2D elements. All right, so second 2D, linear rectangular, we're going to do these types of elements in local coordinates first. All right, so one-dimensional solutions are approximated by line segments. So that's what we've already done. Two-dimensional solutions are approximated by plane segments. All right, so here's our plane segments. So we have globally in the x and the y directions. We have an overall length here on this side, width on this side. And we have nodes I, J, M, and N. And then we have a local coordinate system there of x and y. All right, so we have some idea what we're working with here. So before, where it was usually just I and J for linear element, now we have I, J, M, and N because it's a plane element. All right, so temperature distribution here. Again, if we just looked at our elements, here's I, J, M, and N that makes up this overall plane that we're looking at. And if we would plot that temperature distribution, this is what it would look like, for example. So we'd have maybe a higher temperature up here at node N, low temperature down here at M, and then some intermediate temperatures at I and J. It creates this whole plane of temperature that changes across that space. So the approximate temperature distribution in that rectangular element is, so the temperature at any point within the element is some constant B1, B2, 3, and 4 times the x, y, and x times y locations where we're at in that element. So we need to develop those, figure out what those coefficients are, B1 through 4. All right, so those are unknowns. So we're going to need 4 boundary conditions. Guess what they're going to be? Right here, right? So you start here. So the temperature at is equal to Ti at x equals 0 and y equal to 0. So again, here's x, here's y. So this is 0, 0. So that's node I. For J, the temperature at node J here. So we're going to 0 in the y, but we are some distance L over in the x. At M, we're out L and W position, x and y distances. And for node N, x is 0, but L is W, which is the width up. All right, so there are boundary conditions. So we substitute those into our equations, into the equation, and we can create 4 equations with 4 unknowns. You can solve it simultaneously to obtain B1, 2, 3, and 4. So here's B1 is just the temperature at node I. B2 is 1 over L. Temperature at node J minus the temperature at node I. 1 over the width, temperature at node N minus the temperature at node I. And 1 over the length times the width, temperature at node I minus the temperature at node J plus temperature at node M minus the temperature at node N. All right, so we put those all together, substitute them back in, and we can figure out the temperature at any location within our element. So if we know the x and y coordinates, and then here's x and y, right, we can determine the temperature at any point within our element. All right, so if we rearrange this, we can obtain the shape function. So if we rearrange to solve for just the Ti terms, here's Ti, TI, and there's TI, and temperature node I. Now we can get those different shape functions. So here are the shape functions with local coordinates. All right, so the shape function node I, j, m, and n, based on local coordinates of x, lowercase x and y. And that's, again, all the stuff we've done before with 1D. Here's how it looks like when we do it with 2D. All right, we can make this very general, put in our, substitute in our psi. So instead of temperature, we got our psi here for our element. So using the shape functions, we can figure out the psi at any location within the element. And in matrix form, is the second equation set up here. All right, so now let's look at 2D linear rectangular, but now in natural coordinates, not local coordinates, but natural coordinates. So similar to the 1D case, we're going to be in the center, right? That's where our eta and our chi and our eta are going to be located in the center of our element, but instead of the center of our line segment like it was with 1D, it's going to be in the center of the whole plane. All right. So the relationship between local and natural coordinates, we have chi is 2x over L minus 1, and eta is equal to 2y over the width minus 1. So the 2D linear shape functions in natural coordinates come out to be this. Right, so you can check those out, right, in the development. Again, same process as we've done before. All right, so we can notice the shape functions still have the properties retained for even when they're natural coordinates. So the shape function at node I is equal to 1 at its own node. So node I and node 1 gives us a value of 1. And so that's when the chi is minus 1 and eta is minus 1. And the same case for the rest. So you can check those out and see if they work. We also have shape function at node I is equal to 0 at all the other nodes other than I. So node j, m, and n, it's all going to be, shape function is going to be 0. And the same with the other 3 shape functions. And if we add all the shape functions up, we'll get 1. So all those are retained. And there's a process similar to the Lagrange function that we use, again, for 1D case, can be used to generate these shape functions. So I'm sure there's a source online and textbooks that you can find to do that. All right, so let's move on now. We're going to look at 2D quadratic rectangular element. Right, so not linear, but quadratic. And so now we have an 8-node element. You see we have I, J, sorry, these I, J, M, and N. But now we also have K, L, O, and P. All right, so basically as it says here, it's a higher order version of the 2D 4-node quadratic element. So now we can do kind of this curvy, wonky thing here. And it's well suited, as you can imagine, for curved boundaries. So we can get not just have a straight line between M and J, but we can also do some curve with L if it gets shifted out a little bit. So for the same number of elements, this element produces better nodal results than the linear 4-node element. So the 4-node linear rectangular element we just looked at, because it only has 4 nodes, it doesn't really do curves really well, so this one can do that. So it ends up giving better node results if you use the same number of elements. The approximate solution for this element obviously gets bigger, so now we have 8 different coefficients, 2, 3, 4, 5, 6, 7, and 8. All right, wow, that's a bunch of stuff to solve for there. So using boundary conditions, we can solve for those unknowns, determine the shape function, determine the shape factors, shape functions, is a huge task. All right, so it can take a bunch to do that. Can be done though. So for the corner nodes, we have these guys for I, J, M, and N. And for the midpoint, we have these shape functions for K, L, O, and P. All right. So again, using them all the same way as before. So if we go to general notation, we're going to use our psi again. We substitute in our shape functions there with our psi values at each of the nodes. Again, we have it in matrix form. And the shape function properties all still apply here. All right, so pretty straightforward. Again, what we're doing here is just showing this for different cases, a lot of repetition that's going to be happening in the development, showing the shape function and things. So hopefully you get that pattern. So it's just the kind of the nuances of how many nodes do we have and how do we locate them.